talking about errors, precision, and accuracy. Now, when we say error, in the scientific measurements or laboratory measurements or any measurements, errors are bound to occur. Scientists will only try to minimize errors, yet we can't avoid errors in measurements, but we can actually minimize it. Now, there are types of errors. I've talked about relative errors and also absolute errors and how to calculate them. Now, errors basically, looking at the source of errors, are classified to be random errors, which are errors majorly due to human, and then systematic errors are errors due to instruments, and then gross error are errors due to both human and instruments. Now, this is very, very important. We must make sure to avoid systemic errors or systematic errors. The instruments are to be calibrated, should be well calibrated first. And then, to avoid human errors, the scientist or the person take measurements must have the skill, good skill of taking that measurement. With that, we'll minimize random errors and systematic errors. Now, very, very important, we talk about precision. Precision is where we have sets of data. Student A, B, and C are taking measurements. And they are taking measurements of a known quantity. Let's say a known quantity, these 3 students or 4 students take measurements. You discover that all of them are likely to come up with varying measurements of values. Now, that is due to errors associated to that measurement. Now, very, very important, we should understand that when we talk about precision, we are talking about how close are the measured values. How close are the values of the set of measurements. Now, the 3 students or the 4 students who have taken measurements of a known quantity, and they have come up with varying values. What is the precision of that set of measurements? Precision talk about the relationship between the individual measured values. And so, how close are the measured values? That is precision. And then when we talk about accuracy, accuracy will now talk about how close is that measured value to a known true value, or how close is that measured value to a theoretical value. That is what we refer to as accuracy. So it means accuracy is talking about the closeness of individual measurement in a set of measurements, while accuracy is comparing the individual values with a known value, which is referred to as true value, sometimes as theoretical value. That is accuracy. to know the difference between precision and accuracy. Now, we can actually measure precision of a set of measurements, and we can also measure accuracy of set of measurements. And we can compare different set of measurements. We can have up to 3 sets of measurements, and we work the precision of each of them, each of the set of measurements, and compare with other sets of measurements to know which of them have higher precision or which of them has the highest precision. It's very, very important. We can also calculate or work the accuracy of a set of data and compare with another set of data to know which of the measurements are more accurate. It's very, very important. Now, to evaluate the precision of a set of measurements, what we actually use is this. We use standard deviation to calculate precision of a set of measurements. Now, standard deviation, you are familiar with the formula. You work the mean of that set of data, and now you work or calculate the standard deviation of that set of data. And then you go to the next set of data and work the mean and then the standard deviation. Mean is simply the sum of the individual measurements divided by the number of measurements. That is mean. That is mean. Now, you work the mean and you use the mean to work the standard deviation. Now, how do you know in 2 sets of data, or you have 2 sets of data or measurements, how do you compare the precision? You compare their standard deviation. The one with the least standard deviation is the most precise. The one, I repeat, the one with the least standard deviation is the most precise. It means it has a higher precision. The individual measurements are very close. It's closer than the one with higher standard deviation. So we use standard deviation to compare the precision of different sets of data. Now, for accuracy, what you do is simply percentage error. You use percentage error to calculate accuracy. Now, for percentage error, when you have a set of data, and it's not just one data, let's say 3 trials, 3 measurements in that set, what you do, you add all those individual measurements and divide by the number of measurements, which is your mean. That will now form a single number, which will be the experimental value of that set of data. So error, percentage error, is equals to experimental value minus theoretical value over theoretical value times 1000. Now, when you work the percentage error of a set of data, and then you also work the percentage error of the second set of data, maybe up to 3 sets of data. Now what do? You compare the percentage error of these different sets of data. Now, the one with the least percentage error is the most accurate. The set of data that has the least percentage error is the most accurate. While the set of data with the highest or higher percentage error is the least accurate. So the one with lower percentage error has higher accuracy, while the one with high percentage error has low accuracy. If you are asked to arrange sets of data in the order, either descending or ascending order of accuracy, you should be able to arrange them by their values. If it is increasing order, you should be able to arrange them from the one with the least percentage error to the one with the highest percentage error. That is for accuracy. For precision, if you are asked to arrange a set of different sets of data in their order of increasing precision, the one with the highest standard deviation is the one with the lowest precision. And so you start with the one with the highest standard deviation and end with the one with the least standard deviation, because the one with the least standard deviation is the most precise, or the one with the highest precision. That is how precision is compared or evaluated in different sets of values. Here we have table before us with 3 sets of data generated by device A, B, and C, where device A, B, and C were used to measure a known length. Now, each of these devices were used to measure the known length 4 times, so it has generated this data table. Now, we have the task to find out which of the devices is of the highest accuracy and which of these devices is of lowest accuracy. We have a challenge to find out. Now, applying what we've been taught, how to determine accuracy and precision. Now, at this point, we need to work out the mean of each of these devices. When we work out the mean of each of these devices, then we can proceed to calculate percentage error. Now, percentage error. Now, percentage error is equals to experimental value minus true value over true value. E is the mean of the set of data which has been calculated from the table. The true value is T. Percentage error should be always reported as absolute value which means you ignore negative sign where the true value is greater than the experimental value. Now here, using the formula, percentage error is now device A 16.26%, device B 0.81%, device C 0.81% also. Now you can arrange them in increasing order of accuracy. In that case, you begin with the one with the highest percentage error and end with the one with the lowest percentage error. Now it then means that now device A will be first, then followed by device B, then C, being that C and B are equal. Volume reading. Now in the laboratory, understanding volume reading is very important. Two things to understand is number one, graduation subdivision. Number two, precision or accuracy of the measuring device. These two are key. Graduation subdivision GSD is equals to interval difference D over number of subdivisions N, which is GSD equals to D over N. While precision accuracy is equals to GSD over 2. This is a section of a graduated glassware. Now look at the measure line, in this case below 23, and then you see sub measure line at the center between 23 and 24, and then 24 you have a measure line again. So the lines in between are the lines called the subdivisions. Those are the subdivisions. Now the challenge we have or students have is, what does each of these subdivisions represent? In this figure we have 100 milliliter measuring cylinder, a section of 100 ml measuring cylinder. Now we want to know what each of the subdivisions represents, meaning each of these lines, what does they represent? Being that only the measure lines are numbered while the subdivisions are not numbered. Now what we need to do to know what the subdivisions represent, we take an interval. In this case, I now take an interval 90 to 100. Now 90 to 100, that will give us an interval difference of 90 minus 100, which will be equals to 10. Then the next thing I will do is, what are the number of subdivisions between 90 and 100? Now I will now start to count the intervals beginning from 90. Now starting from 90, the line above the measure line at 90 is 1, 2, 3, 4, 5 at the sub measure line at the middle, then 6, 7, 8, 9, 10. This is at exactly 100. It means I have 10 subdivisions. So the number of subdivisions here is equal to 10. Here GSD being interval difference over number of interval will now be 10 divided by 10, which will now be equals to 1 ml. It means that each of the subdivision here in this 100 milliliter measuring cylinder represents 1 milliliter. 1 milliliter. That is the subdivision of the 100 milliliter measuring cylinder. We can now proceed to calculate the precision of the measuring cylinder, which is also referred to as the accuracy. Now, the precision or the accuracy can be calculated this way, as we have earlier discussed also in the formula here, that is graduation subdivision divided by 2. In this 100 milliliter measuring cylinder, our graduated subdivision was 1 ml, which is 1 milliliter. So now, if that's the case, our precision or the accuracy of this device will now be 1 divided by 2, which will be equals to 0.5. This precision or the accuracy of a measuring device can also be reported as plus or minus. In this case, it can be reported as plus or minus 0.5. Now, looking at this precision, you see that it's in first decimal place, just 1 decimal place. It means that any result from this device or measurement from this device can only and always be reported in first decimal place. You can't report it less than first decimal place. You can't report it more than first decimal place. It must always be reported in first decimal place. Let us take another example. Now, this is a 100 milliliter measuring cylinder. The red mark here is the level of the solution. Now, what is the reading of the solution in this measuring cylinder? Now, we have earlier calculated the subdivision to represent 1 milliliter. Now, the red mark is above 90 but below 100. So, being that each of the subdivision represents 1 milliliter, we can start counting from 90 upward to know what the level of the liquid is. Now, let's count. From 90, the measure line at 90, to the next subdivision 1, the next one 2, the next one 3, the next one 4, is at the 4th subdivision above 90. Since each of the subdivision is 1 milliliter, we can say 91, 92, 93, 94. So the reading of this solution in this measuring cylinder is 94. But you can't just report it as 94. To report the reading, you must consider the precision, which is the accuracy of this measuring cylinder. Now, the accuracy or the precision of this measuring cylinder, as we calculated, was 0.5. So, being that is 0.5, now it's in first decimal place. So, you will report this result in first decimal place. So, this 94 can be reported or be read 94.0 milliliter. 94.0 milliliter. That is the correct reading of the level of the solution in this measuring cylinder. Let's take another example. This time around is a sample of 50 milliliter Burette diagram. Now, you must first know the graduated subdivision, then also the precision or the accuracy of this Burette. Now, before you can take reading or make reading on this Burette, now as I've earlier said and explained, we take an interval, and here let me take an interval 2 to 1 or 1 to 2. Now that will now give me interval difference of 1, because 2 minus 1 will be equals to 1. Now between interval 1 and 2, how many subdivisions are there? As you count, you see that we have 10 subdivisions. 10 subdivisions. It then means that we can now go ahead and work out the graduation subdivision. Now, what is subdivision stand for? Will now be the interval difference over the number of subdivisions in that interval. So now, being that the interval difference is 1, the number of subdivisions between 1 and 2 are 10. It will now be 1 over 10, which will be equals to 0.1. That in this case, it means that each subdivision in this Burette represents 0.1 milliliter. 0.1 milliliter. Now, the graduation subdivision is known, which is 0.1. We can go ahead and calculate the precision or the accuracy of this Burette. Now, the accuracy will now be the graduation subdivision divided by 2, which should be equals to 0.1 divided by 2, which will be 0.05. 0.05. That is the accuracy or the precision of this Burette. Now, this can be reported as plus or minus 0.05. Now, 0.05 is in 2 decimal places. Is in 2 decimal places. It means that any reading taken or being read from this Burette can only be reported or read in 2 decimal places. Can only be read or reported in 2 decimal places. Now, let's see how we can take reading from this Burette sample. Now, A is a level of solution after first titration, and B is a level of solution after second titration. What are the readings on A and B? Now, previously we have calculated that we have known what each of the subdivisions represent, which we said is 0.1 milliliter. Now, so the first titration, which is at A, is below 1. Remember, for Burette, you see that the highest mark on top there is 0. The graduation is up down, while measuring cylinders, the graduation is down up. So you are taking the reading from the top downward. Now the mark is below 1. Now it means it's beyond 1. Now we now need to make reading. Now we can count from the measure line 1. I've earlier said if you are counting, you are not counting the measure line you are beginning with as 1. Between the measure line you are starting with and the next subdivision is 1. Those small intervals is what you are counting. So now we go now from 1 to the first subdivision is 1, the next one 2, next one 3, the next one is after 3, which are the line lies between 3 and 4. So it's relatively at the center. So what we will now estimate here to be half of the interval between those two subdivisions. So it should be 5. So in this case, since each of them is 0.1, half of 0.1 will now be 0.05. So now it will now be 1.35. 1.35. That will be the reading of A. B, which is the reading at B, is for your practice. Please make sure you attempt to take the reading. Practice make perfect. Now let's look at mass measurements. Now we have extensively looked at volume measurements and how we can take readings and report correctly. Now the principle of precision accuracy also applies in the case of mass measurements. As we calculated the precision, the accuracy of the measuring device, which is the volume measuring device, the same thing is applicable in the case of mass measurement. But the case of mass measurement is self-determined. It's very simple. Now, as you on the weighing balance, you press the off and on button and you allow it to boot and stabilize. Once zeros appear in the weighing balance at the screen, now what to know the precision of that weighing balance or the accuracy of that weighing balance, you look at it. Is there the zeros? How many zeros do you have after the dots? How many zeros do you have? Some weighing balance might not have dots, decimal places, might just have 0 appearing there or 00 appearing there. But if you have a dot, then you should count the number of zeros after the dot. That indicates the number of decimal places. Assuming you place a sample on this weighing balance and it reads 2 on the dots. Now, before you report that value correctly, you should know the precision of this measuring device. I've told you earlier that you consider the decimal places. Now, in this measuring device is 0.00. It's in 2 decimal places. Now, the precision is plus or minus 0.01 is the precision or the accuracy of this measuring device. In this case, the precision or the accuracy is in 2 decimal places. So reports for or measurement from this weighing balance must always be reported in 2 decimal places. So the object you place, the sample you place on it that read 2 on the dot should be reported 2.00 grams. 2.00 grams. That is the right way of reporting data from this weighing balance. Let's talk about uncertainty in measurement briefly. Every measurement, there is some level of uncertainty. Now, that can be determined from the precision or accuracy of that measuring device, which we have extensively considered how to know the accuracy or the precision of a given device. You can know the uncertainty of that device you are using to measure from the accuracy value. For instance, you have a measuring device whose accuracy or precision is plus or minus 0.05. This means that the uncertainty value of this device is 0.05. Now, it means that any measurement you take from this device is either that measurement is 0.05 above the reading or 0.05 below the reading. Assuming you are taking measurement from a device whose precision or accuracy is 0.05 and the reading happens to be 25.00 milliliter, which is in volume. Now, it means that this reading of 25.00 ml, the level of uncertainty, this value is either 0.05 milliliter less than or 0.05 milliliter greater than the 25.00 milliliter you are reporting. That is the uncertainty of the measurement. Even though you are free to report exactly the reading on the device, you should bear in mind the uncertainty in that measurement. Also, for mass measurement, the weighing balance with precision or accuracy of 0.01. Now, if the weight placed on it reads exactly 2.00 grams, that reading, the uncertainty associated to it is that is either is 2.01 or is 1.99. That is the uncertainty of the reading of that weighing balance. Due to the uncertainty of measurements, the last digit of every measurement is not certain. I repeat, the last digit of every measurement is not certain. In data reporting, sometimes data are reported as this form. where the last digit is reported like a superscript. Now, whenever you see any reports in this form where the last digit is presented like a superscript, it's noting the uncertainty that the last digit is not certain. Now watch out for the next video on decimal places, significant figures, and rounding off. That is also another key area in data reporting in science laboratory. Please watch out. Please, after viewing, don't forget to like, subscribe, and press the notification button for the next upload. Bye.